So in today's video, we're going to take a look at the derivatives of inverse trig functions. I'm only going to prove two of them because otherwise this would be quite a long video, but you can use the same principle to kind of prove pretty much all of these inverse trig derivatives. So let's go ahead and start off with the derivative of arc sine of x, or inverse sine of x. And the way that we would approach this is kind of the same way that we approach the derivatives of inverse functions, like general inverse functions. So we can set y to be equal to arc sine of x. And then what we can do is we can kind of get rid of this arc sine by just taking the sine of both sides, right? So we'll end up with sine of y is equal to sine of arc sine of x, or sine of sine inverse of x is just going to be x. And then what we can do, if we want to find the derivative, we can essentially just apply the derivative operator to both sides, right over here. Keep in mind it's the derivative with respect to x. And then we will end up with the derivative with respect to x of sine of y. We know that sine of y is a composition of functions, right? We have the sine function over here, and we're inputting y into sine of x. And so as a result, we're going to have to use the chain rule. And so what we're going to do is we're going to multiply, first of all, we're going to take the derivative of the outer function, which would end up being cosine of y. And then we're going to multiply that by the derivative of the inner function. The inner function is y, and so the derivative with respect to x of y is just dy by dx. And we know that the derivative of x is just going to be 1. And then finally, we can divide both sides by cosine of y, and we're actually nearly done here. And so that's just going to be 1 over cosine of y. But we know that cosine of anything, so we can say cosine of theta, is just the square root of 1 minus sine squared of theta. And this just comes from the Pythagorean identity. So this is equal to 1 over the square root of 1 minus sine squared of y. But what is sine of y? Well, we said that sine of y is just equal to x. I don't know why I spaced out there for a second. So sine of y is equal to x. And so we can essentially just replace this sine squared of y with just x squared. So we'll end up with 1 over the square root of 1 minus x squared. And that would be our derivative right over there. And you can actually use the same process to determine the derivative of arc cosine of x, and you should end up with negative 1 over the square root of 1 minus x squared. And I'm going to leave this one to you to actually prove because it's basically the same exact concept. With respect to arctangent of x, we're just going to go ahead and use the same principle. So if we let y equal to tangent inverse of x, I'm just changing notations over here, then we'll end up with tangent of y is equal to x. We can take the derivative of both sides, and we'll end up with the derivative with respect to x of tangent of y. We know that this is, again, a composition of functions. We have y being input into tangent of x, and we know that the derivative of tangent of x is just going to be secant squared of, keep in mind, we're not inputting x, instead we're inputting y, so it's going to be secant squared of y times dy by dx equals to the derivative of x, which is just 1. And then again, we can divide both sides by secant squared of y. We'll end up with dy by dx equals to 1 over secant squared of y. But we know that secant squared of anything, we can say secant squared of theta, is going to be equal to 1 plus tangent squared of theta, right? And so if we were to input, instead of theta, if we were to input y, then we would just end up with 1 plus tangent squared of y. And we know that tangent of y is equal to x, so we can just substitute tangent squared of y for x squared. So we'll end up with 1 over 1 plus x squared, and that would be the derivative. And again, you can do the same process to determine the derivative of arc cotangent of x, and you'll just end up with the negative of this result over here. And we do have the derivatives of arc secant and arc cosecant, but I mean, these ones are a little bit outside of the scope of Calculus 1, but they are a pretty interesting kind of derivation if you want to go through that on your own. I wrote the final results out over here, though, if you essentially care about that. But these aren't really important right now for AP Calculus, AB, or even IB mathematics, because you don't really cover these ones too much. But nonetheless, still pretty interesting to derive.